Oh. Hi, I'm Tony, and I made a self-balancing robot. The self-balancing robot is just an inverted pendulum. What it is a mass M on a solid rod H, and when the rod is being tilted by an angle theta, the robot will move forward into that direction and basically try to rebalance itself back to its original standing position. The first question that I had is whether I should make the robot tall or short. You can see that the torque created by the gravity of the robot is equal to mgh, the sine of theta, and that is approximately mgh theta when the angle is less than 10 degrees. And the moment of inertia of the robot can be approximately mh squared, because this is a point mass being h far away from the rotational axis. So you can see that the angular acceleration in this case, which is tau over I, the torque over the moment of inertia, will be equal to g theta over h. That means that if we make the robot taller, which makes h bigger, then the angular acceleration will be less, which means that it will accelerate angularly at a slower pace. That means we have more time to react to the change of theta. In other words, make it taller. If you take an umbrella when it's extended, then it's easier to balance on one hand. Yep. Then when it is short, let's talk about the components of the robot. So what we have here is an Arduino Uno, two DC motors, they are 12 volts, motor driver, which is just an H bridge, the L298N motor driver. We will drive the two motors. In here, this is the accelerometer and gyroscope sensor module, the MPU6050. We also have a Bluetooth module, HC05, in here. That's being plugged on the breadboard and then being connected to Arduino as well. And we use the Bluetooth module to actually control the robot wirelessly. And up here is just a LiPo battery, the 11.1 volt LiPo batteries. And that's it, that's the robot. The second big question is, how do we actually control it? And for that, what I'm using is called the PID controller, which is a closed-loop feedback system. So first of all, you have the reference angle, which is 0 degrees, because we want the robot to stay vertical. You minus the current angle, which is the angle that the robot is currently at, and you get the error. You put that error into the PID controller, you get the control signal for the motors, and that will affect the current angle. And that new current angle will get feedback back into the loop to calculate new error into the PID controller. And this process repeats itself continuously to stabilize the robot. And if we tune the three gains KP, KI, KD just right, then we might get the output result to be like this, where the angle theta initially when the robot is being tilted from an angle away from its standing position, over time it will come back to zero and straighten out. For more information on how the PID controller works, just click on this video.
Oh wow. Oh no. Chill. Chill. Oh shit.
So, starting this project, I set out three nodes. I will not be using the Arduino IDE because it sucks. What I'll be using is the Arduino Studio. It's just a much better IDE. Second thing, no libraries. So I will be working on the hardware of the Arduino itself and without relying on any libraries for the input and output, PWM, everything. I2C, UART for the Bluetooth, no libraries at all. And instead, we will use the datasheet. We use the datasheet to check out all the registers and the bits on the register and how to work on them instead of using any pre-written libraries. We will write our own libraries. And the third no is no sleep. Of course, because how are we going to do this without staying awake late at night? This has been Tony. Thank you for watching and see you guys in the future.